All right. So one of the things that I really want to emphasize is kind of how the nature of science plays into the way that we can approach evolution. So one of the things that I like to emphasize is the idea that science is really not any kind of search for the truth. We say that sometimes, like you'll hear people say that, well, science is truth, or science is, real, or whatever, but the reality is more complicated. Really, all we want to do with science is explain the stuff that we see by using data, measurements, observations, numbers. Things like, well, there's more dark moths now than there were 10 years ago. What's the deal? There are more mosquitoes now that are resistant to DDT than there were 20 years ago. What's the deal? When I pick up this ball and drop it onto the table, it goes down. What's the deal? So we use data and we use observations to come up with explanations. So we match things like, well, the moths started to become more dark in appearance at the same time that the trees started to become more dark in appearance. So there's a connection there, and maybe it has something to do with camouflage and predation. And this ball is moving down toward the surface of the Earth, and the ball has mass and the Earth has mass, and so maybe those two masses are pulling on each other. Could we do anything with that? And then based on our explanations, we try to make some predictions. Well, if the reason that mosquitoes are resistant to DDT is because we're spraying them with DDT and not all of them are dying, and the ones that survive are genetically resistant, then one of the things we should see is that in areas where DDT isn't sprayed, those mosquitoes shouldn't have DDT resistance. We go and we test, and if our predictions are successful, then we start building our scientific theories about how these things work. If when I drop the ball, it moves toward the Earth because the Earth and the ball both have mass, then I should be able to look at other things too and say, well, maybe other things will fall. And so yeah, this lead weight does fall. And we ought to be able to make measurements and predictions about how fast things are going to fall and how much force is being exerted on them when they fall. As we test those things over and over and over again, we build our understanding of how we can use those explanations and observations to make useful predictions. And what's really unique about science is that we are constantly seeking to disprove our own ideas. That's how we came up with new ideas about gravity. We realized it's not just a pulling force between two masses, because if it was a pulling force between two masses, then we'd see certain planets move in ways that they don't move. It's off by a little bit. But if it turns out that actually those planets are moving in a straight line through distorted space-time, then they move exactly. Then we would predict they would move exactly the way that we do. We have revised our ideas about evolution as well. One of the big things that people thought at first was that, well, it's always this gradual change. You see these tiny little incremental change in organisms, just like our baby pictures going day to day to day to day to day. Well, it turns out that's not entirely true. We know now that there are lots of organisms, lots of times in evolutionary history where there were major changes that happened really quickly. It's kind of like the equivalent of going outside and looking at the ground and it's just bare dirt, it's just bare dirt, it's just bare dirt, and then one day you come out and you see a seedling. That happened overnight. So if you took a picture the day before, there would be nothing. The next day you take the picture, there's a seedling. That would be a really clearly visible difference. So if our observations don't match what our predictions say they should, we change our explanation. We have to. And there are rules to science, and those rules are there not just arbitrarily. We don't just say science has to be this expensive, or you have to be this tall to collect data, or whatever. What we do with science is we say, since we want our explanations to be useful, we need, for example, to rely solely on natural causes. Because if we were to say, well, here's the thing about gravity, is it's actually invisible elves pulling down on things with invisible strings, that doesn't help us a whole lot in terms of making a prediction, because we can't we're not gonna be able to say like, well, the elf is always gonna be standing over here or always gonna be standing over here. Like, we just can't really predict anything about invisible elves pulling down on things with invisible strings. So instead, we try to limit our explanation to things that we know occur in nature, things that we can see, things that we can manipulate. And that may not be right, and it doesn't have to be right. It just has to work. Just like our model for gravity just has to work. As long as I can predict how long it's gonna take for something to fall a certain distance, we're good. It doesn't really matter if it's moving through distorted space-time, if it's being pulled towards somewhere because of an attraction between masses, or if it's an elf with an invisible string. Either way, if I can make the prediction, the science is useful. And that's really what we're gonna focus on when we're working with evolution.